Now, in this video, we would like to discuss the explanation that was given by Albert Einstein, and that was basically it was Einstein who explained the strange behavior of photoelectric effect that we have discussed in the previous videos, where we found that there was dependence of frequency. There was dependence of the threshold frequency on photoelectric effect to take place. So what Einstein did, he came up with a solution. He came up with a simple explanation of this emission of electrons from photosensitive metals, and what Einstein did, actually, he extended the Planck's quantum theory of radiation to explain this photoelectric effect. And Einstein's theory is purely based on Planck's hypothesis, Planck's quantum hypothesis. Now, what are those hypotheses that are inculcated to explain the photoelectric effect? The very first important point is that the energy of this electromagnetic radiation is not continuous. The energy that it has, it's not continuously distributed like this, like that of a wave or a matter wave, but it remains concentrated in some form of packets, right? Packets of energy. And this packet of energy is h nu, and h nu is this packet of energy. So there are discrete energies involved in the Planck's hypothesis that are being used here. And this nu is the frequency. It is the frequency of radiation, and h is known to us. It is the universal Planck's constant. Now, these packets of energies, they are called quantas, or they are called photons that we have already talked about. So we call them as photons or quantas. And obviously, the photons have a small energy content for light of low frequency, and they have large quantity of energy for high frequency. That should be the case here. The next important assumption that I should say is that each packet of this energy that we have h nu of this energy is so concentrated that it can transfer its whole content. It can transfer its whole energy, the whole content it has, to one electron. So in other words, in photoelectric effect, one photon is completely absorbed by one electron, which thereby gains the quantum of energy and may be emitted from the metal. So it's purely absorbed by electron. So the next important assumption here is that the photoelectric effect is the result of basically the interaction of this single photon with an electron which is bound to the surface of this metal. So these three assumptions, these are the basic assumptions that were used by Albert Einstein, extended the theory of the quantum theory of Planck to explain the photoelectric effect. Now, according to Einstein, what Einstein believed is that when a photon of energy, say h nu, when the photon of this energy is incident on some, say we have a metal and falls on a metal surface, its entire energy is transferred to the single electron here. right, in the metal. The energy of the photon goes in two dimensions. It goes in two parts, basically. A part of this energy is used to eject the electron from the metal surface. And this energy, the work that's being done to eject this electron out of this metal surface, we call this as work function, right? And the remaining energy, the other part of the energy that's being absorbed by this electron, this energy appears in the additional kinetic energy that the electron has. If you go back to that experiment, the electrons are not only ejected from the metal surface, they have acceleration, they have motion. And then we have anode here, and this anode is catching these electrons. So what is proposed here, that the energy that this electron absorbs, it goes in two parts. One is to eject, and the other part is transferred to this electron in the form of kinetic energy. So to move on from here is we can analytically represent this thing. Suppose so we have a photon having energy h nu, and a part of its energy is used to eject this electron, and this work is defined as work function, and the rest is given in the form of kinetic energy. The additional kinetic energy is given to the electron. So this h nu, which is being completely absorbed by this electron, gives us the measure like this. So if I go with this k, it will come out to be h nu minus this work function. So this w is nothing but work function. Okay, now we can look for things here. Is that this work function, or its value is different for different metals. Okay, this equation that we have here, I call it as equation 1. This equation is called as Einstein's photoelectric equation, and this equation purely predicts all the experimental results of photoelectric effect that we have discussed in the previous videos. It explains everything about whatever the observations we used to have in those videos. Now, the point is that the maximum kinetic energy that increases with the increase of this kinetic energy, it increases with the increase of frequency, and decreases with the decrease of frequency. This kinetic energy increases with the increase of frequency. It decreases with the decrease of frequency of incident light. And finally, a stage comes when some maximum kinetic energy becomes zero. The maximum kinetic energy that we have, it becomes zero at some frequency, for the particular frequency. Now, the frequency of incident radiation at which this kinetic energy of the emitted electron is zero, that frequency is referred as threshold frequency. We call that frequency as threshold frequency. So at threshold frequency, the maximum kinetic energy, the kinetic energy of the electron is simply zero. The maximum kinetic energy of this electron is zero. So there is no point of ejection at this frequency, and at the same time, this work function can be defined in terms of that frequency that we have defined as this threshold frequency. And since we are talking in terms of Planck's packets, so that will be h nu naught. So for this W, we have h nu naught, where this nu naught is nothing but the threshold frequency. So obviously there exists this threshold frequency, and when the photon of energy which is just sufficient to overcome the binding energy of this electron, which is in the metal, right? When it's able to overcome that binding energy, this threshold frequency will depend upon the work function of the particular material. So different electrons in different materials will have different binding energies. So different materials will have different values for the work functions, values for energy that's required to eject the electron from metal surfaces. And if the frequency of the radiation is below that minimum frequency that we talked about, then there will be no emission of electrons. So if we have that nu naught and we have that nu dash less than this nu naught, there will be no emission of electron. The electron will not be emitted. Now, and increase. Suppose at this stage we increase the intensity of the radiation, we increase its intensity. What increase in intensity is going to do here? It's going to increase the number of photons. It's going to increase the number of photons, and every photon has the same energy, that is h nu. And if the nu associated with this energy is less than nu naught, even though you increase the intensity of the photons, that's not going to give you any photoelectric current. And that should be clear from this condition now, right? So increasing intensity will yield no results. It's not going to give us the emission of electrons. So now, if we go back to this equation, what we have is the kinetic energy is equal to h nu minus h nu naught. Okay, so because this h nu naught, as we defined it in terms of the work function, and this nu naught is the threshold. Is the threshold frequency, and this equation will give us the measure of maximum kinetic energy of the emitted electrons. And electrons which are emitted at lower energies may have suffered collisions inside the metal before leaving the surface, or may initially have had a binding energy slightly larger than that of W. Right? Now, in terms of the threshold frequency, we have this equation and we have the maximum kinetic energy, right? And if I define stopping potential at this stage, now what is stopping potential? If we go back to the experiment, we have electrons, okay, they are moving under the potential difference. We have light ejecting electrons, and we have the potential difference V. Now what we do is we reverse the voltage, and on reversing the voltage, this gets negative charge. So electrons are repelled, and a maximum a stage comes when the stopping potential is completely able to stop the electrons, seize the motion of electrons. So at that time, the maximum kinetic energy that electron has, this maximum kinetic energy will be equal to the stopping potential. That will be EV. So here we can write down the Einstein's photoelectric equation, which purely explains photoelectric effect in terms of stopping potential. So I can write here EV naught is h nu minus h nu naught. Now, before proceeding from here, if I go back to this equation, k equal to h nu minus nu naught, here it's clear if nu is less than nu naught, kinetic energy is negative. So it's meaningless. We cannot have negative kinetic energy. So no photoelectric effect is going to take place if nu is less than nu naught. For the same case, if nu is equal to nu naught, again in this case we have k equal to h times nu minus nu, and thus k will come out to be 0. So again, in this case, there will be no photo emission of electrons. The electrons will not come out, right? But if this nu is greater than nu naught, in this case, this kinetic energy will be positive. It means the electron will come out and we can measure the current in the experiment. We can measure the photocurrent in the experiment. Now, to proceed back from this equation, come back from this equation, what we have is EV naught is equal to h nu minus h nu naught. And what we can have here is, if I write V naught is h by E nu minus h by E nu naught. You can write this equation like this, right? And this equation is the equation of a straight line. So from this equation, if I correlate it with, so here we can see if we have a graph, and that graph can be we can extend that graph to a faithful meaning. In that case, the slope of that graph that we will have, it will be like this, and suppose this is theta, and this will be, the slope will be h by e. Now, the slope here can be simply tan theta. So tan theta will give us h by e. So we can calculate the value of this Planck's constant, that is E tan theta. So this way, photoelectric equation was, Einstein's photoelectric equation was completely able to demonstrate, explain the photoelectric emission, which could not be explained by the classical electromagnetic theory. And classical electromagnetic theory completely failed to explain the phenomenon of photoelectric effect. And it was Albert Einstein who extended basically the Max Planck's quantum idea and used those, came up with some basic assumptions, and could fully explain the observations of photoelectric effect. And for explaining this effect, Albert Einstein was awarded a Nobel Prize.